3, 2, 1.
Got a blast!
To the stars, you'll buy candy bars. Rides a kid with a knack for invention. With a superpowered mind, a mechanical canine. He rescues the day from sure destruction. This is the theme song. Go Jenny Neutron.
Welcome to the Expanding Universe.
I'm Ryan Marciniak.
I'm Jesse Robertson.
Let's get right to it.
Okay, we are talking about gravitational waves.
Why are we talking about gravitational waves?
Not gravity waves.
Yeah, right?
Gravitational waves. Because scientists decided that the two words should be very similar to each other and describe completely different things.
Yeah, which is really funny because I didn't learn that until gravitational wave stuff started coming out with LIGO and Virgo.
Well, that's because it doesn't matter, right? You learn gravity waves back in that was back when we were doing general relativity together in undergrad. You learn what a gravity wave is.
I don't think I learned it back then. You know,
we must have.
Wait, gravity waves. Okay, what do you think gravity waves are?
Okay, a gravity wave is the way in which gravity transfers its information from one spot to the next. So when an object is moving through space, you don't instantaneously feel its gravity the closer it gets. You feel it takes the speed of light, it takes the light travel time for the information to get to you that something is there. So for instance, if you took the sun out of the solar system, we wouldn't know for 8 minutes, and that information is transferred to us via gravity waves.
Interesting.
Am I wrong?
Well, I don't know. I never thought about that because when I looked at gravity waves, it's a fluid dynamics thing that often comes up in weather.
What?
Yeah.
Okay, now I have to Google it.
So yeah, okay. So here's my spiel. Gravity waves form in the atmosphere as a result of destabilizing processes. So at weather fronts. And it's actually a thing that has to do with fluid dynamics. So gravity waves are waves they're generated in some fluid at the interface between two mediums where gravity or buoyancy is trying to restore equilibrium. And that's not me making that up. That's just me reading off of this page. But an example is the interface between the atmosphere and the ocean, which gives rise to wind waves.
Okay, I know where I went wrong on this. The word I was looking for was graviton.
Oh, the particle.
So this is where my confusion came in. So a graviton is the particle that transmits the gravity information.
It's a force particle,
I assumed
right?
that the graviton particle would also act like a wave, like particle-wave duality type thing, and then I assumed they were gravity waves.
Interesting.
But
that's great. We've parsed this out. Gravity waves are a thing of fluid dynamics. The graviton is a force carrier particle for the gravitational force.
In the standard model.
Yes, in the standard model, which we could go into an entire other episode.
That's a whole episode
on
for sure.
The standard model of particle physics. And so a gravitational wave then is the distortion of space-time by interacting masses.
Yeah.
I know that took a very long time
I was on
to
the
say.
edge of my seat.
I know, right? I imagine everybody is on the edge of their seat who's listening to this, which right now is nobody.
Yeah, that's okay.
That's all right. So far we've only been able to find the strongest gravitational wave ripples, as it were, the largest distortions, and that's natural, right? Whenever we discover something new, it's usually the strongest, the most powerful, the loudest, the most energetic, But the idea,
All of those describe me.
there you go. So you were the first of your kind. But the idea behind
I'm
gravitational waves is that they're happening all the time, everywhere. Even any amount of mass or any interaction creates these ripples in space-time, but they're so mind-numbingly tiny that we can't detect them. However, now that we have gravitational wave observatories like LIGO and Virgo, we can see the most energetic interactions that create gravitational waves, such as the collision of black holes, or in this case that we're going to start talking about, two neutron stars.
So in this case, we have these two neutron stars that have merged together. They were a binary system, two neutron stars that were rotating around each other. And the thing when you're thinking about gravitational waves and you're trying to get someone to understand about gravitational waves is the idea that the universe is not an empty thing. I think you and I are probably pretty used to the idea that space is a fabric, that it is a space-time reality. This idea that in between us and the planets, where we think we have space, quote unquote space, it's actually there's a space-time fabric, a space-time energy, a web that that permeates the entire universe, and in that fabric there are distortions, and those distortions are predicted by and described by Einstein's theory of general relativity, that a mass in the universe will distort space-time, kind of like, the common explanation is, imagine a 2D surface that is like a trampoline, and you put a ball in it, and it deforms around the ball. You just have to imagine that in 3 dimensions.
Oh yeah, no problem.
Which is, I do it all the time.
Well, the typical thing that people ask when you're trying to explain something like this is how do I know? How do I feel that? Like, doesn't that only happen on the largest scales? And the answer is no. We feel it as gravity, right? That's what we feel as the force of gravity. Is we have lived our entire lives in a curved space-time. In fact, space is much more curved where we are on the Earth than it is out in outer space where there's less mass.
Holy crap, that's so weird.
I know, it's weird to think about, right?
It is really weird to think about.
Yeah, and so these ripples, I often think about it like, the natural way to think about it is like dropping rocks or dropping something in a pond of water, and you get ripples kind of moving outward. And that kind of describes how they get smaller over time, right? If you drop a rock in a pond, right at the center where you drop that rock, there's going to be a big ripple, lots of energy, all the energy, and then as it radiates outward, those ripples get smaller and smaller and smaller until they look like they pretty much disappear. And that's kind of the analogy for gravitational waves, is that energy, just like with a star, gets spread out more and more and more as you go further away from it, and the intensity decreases, right? Usually 1 over r squared, or I guess a little bit more for a spherical system. But the idea is that these are happening all the time. These gravitational waves are all over the place, all over the universe. They're constantly ripples and interacting and passing each other, but they're so tiny we don't see them, and only the largest ones are visible, like the black hole merger. And those, what was it, 2 years ago now? Was the first?
Yeah, just over 2 years.
Yeah, there you go. Was the first confirmed detection of gravitational waves, and that was because of 2 massive black holes colliding 3 billion light years away.
Is that how far it was? I forgot what the distance was.
It was far, yeah.
That's like a quarter way across the universe.
It's a significant distance away and a significant time ago.
It makes you wonder. So as you're saying, there's this 1 over r squared rule, meaning if you get 2 times further away, the energy of the ripple is 4 times less.
Yep.
So imagine how strong those ripples would have been if you were there.
Oh, unbelievable. The big thing that stuck out to me is that when these 2 black holes merged, 3 times the mass of the sun was instantly turned into gravitational waves.
Holy.
Yeah, 3 entire suns worth of mass was turned into pure energy in the form of gravitational waves. But and here's this. I was actually reading something about that the other day. It was like if you were the Earth-Sun distance, one astronomical unit, 150 million kilometers away from the black hole merger, what do you think the ripple would be? Like, how big do you think the ripple in space-time would be from the gravitational wave?
I don't know. I have no idea. I don't know. The size of a mountain.
Okay. So like the wavelength would be the size of the mountain.
Yeah, like a few kilometers.
Okay. So that's not bad. The distortion would be about 1 micrometer at your body.
What?
Yeah.
That's it?
Yeah.
So to put that, what that means is, so this is the key. This gets at how we know that they've happened, right?
Mm-hmm.
So the wavelength of the distortion would be 1 micrometer, which is 1/1,000,000th of a meter.
And that's space
Right?
itself. Yeah, that's 1/1,000,000th of a meter, space itself compressed and then expanded. Bing, bing.
Yeah. So
just
if
like
you
that.
had, if you were holding a ruler, like a meter stick,
Yeah.
It pointing directly at the sun when this release of gravitational waves happened, if you're pointing directly at it, and someone else was holding a exactly the same meter stick at perfectly perpendicular to yours, right beside you, so basically parallel to the sun, to where the energy is coming from, you would see, if you could, the meter stick you're holding that's pointing at the sun shrink by 1/1,000,000th of a meter, while the other ruler stayed the same.
Stay the same along its length. Yeah.
Yeah.
But that's so. I mean, you're not going to see anything, and that's even 1 astronomical unit away. That's very close to this collision, as opposed to us being 3 billion light years away, which is billions and trillions of times further away. And so when those gravitational waves reach the Earth, you got something like LIGO, which detects gravitational waves on distances that are 1,000th the width of a proton.
That's incredible. I've read about this before, but the way you're describing it is like just puts everything back in perspective. It's incredible how precise this instrument is. The LIGO instrument is. It's to be able to measure something on that scale definitively, not just measure it as like some small little blip, but like with a specific precision. That's incredible that we're able to make something like that.
Well, and it just got better. They just finished upgrades on it, which is why we're able to detect now a slightly less energetic thing than 2 black holes colliding, 2 neutron stars colliding. So, I mean, for some perspective, the black holes that collided back 2 years ago were 29 and 36 times the mass of the sun. Right? They're black holes. They're gigantic. They're massive. They're compact. They're what we think of as the heaviest things around, the densest things around. Neutron stars, by comparison, and the neutron stars that collided in this recent detection were only about 1.5 and 1 1/3 solar masses.
Oh, they were much smaller.
Much smaller. I mean,
Yeah.
for one thing, you need lower masses in order to actually have a neutron star and not collapse
True.
into a black hole, which we'll get into. But the other thing is that, you know, this is now kind of the normal detection that we're going to start to see. And I liken it a lot to planets, right? The last revolution 20 years ago of almost 30 years now. Oh my God. The last revolution of science and instrumentation for me was exoplanets. And what were the first exoplanets that we discovered? They were massive planets, bigger than Jupiter, very close to their star. And then as time went on, our instruments get better. We start to find smaller planets that are further away from their star. Right? And so this is kind of the same thing, as you start with the highest energy things, the black hole collisions, and you improve the instruments, you improve the sensitivity, which is mind-blowing considering we're already down to 1,000th the width of a proton. and you start to find those smaller interactions, which in this case is the merger of two neutron stars, which is still mind-numbingly energetic, right?
So that's a good way of looking at it. The way we got really good, like, you it's a proof of concept. So you build your instrument because you expect that there's going to be these kinds of collisions in the universe. Two black holes are going to be merging together, and then you build it to those specifications, and then you do it, and then you say, okay, how can we do better? And that's what they did. Now they're measuring neutron stars merging together. I wonder if they'll be able to make it even better than that, even more precise than neutron stars merging. Let's say to say binary stars merging with each other, where it's even less energetic.
Oh yeah, I wonder. Well, what's next, right? I mean, after that, regular stellar mergers, like maybe in the center of a galaxy, maybe your next step is a typical supernova.
Yeah, because it's got to put some ripples into space-time as well.
Big time. And yet we would consider those really small ripples compared to what we've seen so far. So let's get a bit more into the meat and potatoes of this actual thing.
Wait, do we want to talk quickly about what LIGO is and how it measures?
Sure, why not?
So it's an interferometer, and what that means is so there's a laser beam that is they shoot it at this sort of mirror that's sort of partly transparent but partly reflects the laser. So it splits down two arms. One goes one way and one goes 90 degrees the other way. This one laser creating two laser beams at the mirror. And then it goes and bounces off at the end of the tunnel and comes back. And then when they make it back to the one spot where they split, they merge back together and are sent to a detector. And everything being equal, going down those two arms that are both exactly 2.5 kilometers long, the light will sync right back up with each other, will be completely in phase, and they'll cancel each other out. So you won't notice anything. Now, if the space-time between the arms changes a little bit, then light will be distorted along the pathway, along that arm that it's going, and when it gets back to the sync-up point, it'll be out of phase. And then you can measure the light being out of phase and make a measurement of how much the space-time was distorted en route back. So that's the basis of a laser interferometer called LIGO. And you need really long distances, and you need high precision mirrors and detectors to be able to detect these kinds of very small distortions in the light created by bending of space-time. So there you go. There's LIGO.
Well, the power of LIGO, in my mind, is the fact that they built two of the darn things. Like it's not just enough to say, hey, let's just find $1 billion and build this massive detector with incredible precision in Livingston, Virginia. Let's build another one in Washington.
Hey, government, I want big, huge, massive lasers.
There you go.
Help a brother out.
But the great thing about that is that when you see a detection, you also see it at the other site. And you know that if you're seeing a positive detection at both sites and they agree with each other, as in they are the same intensity, they look the same, that kind of thing, you can independently confirm it. So you confirm that it's a real detection. And not only that, this is the really cool part for me, is that based on the time difference, right? Like the time difference is going to be a few microseconds, if that, between the detections. But because they're in two different spots and they have slightly different times, you can actually figure out which direction those gravitational waves came from.
Are you serious?
Yeah.
It can't be that good. They must have well, I mean, atomic clocks are pretty precise. So if you have the atomic clocks at one at each site, and there you can go down many decimal points on your timer. Yeah, I guess that does seem possible.
Now there's uncertainty too, right? Like there's a huge amount of uncertainty, and actually I'm going to bring that into the conversation because I want to talk about the amazing way that they actually found where these neutron stars collided.
Yeah, this is the good part of this story about these neutron stars specifically.
Right, and it's it starts off with kind of two things. They got this gravitational wave signal, and seconds after that, the Fermi Gamma Ray Observatory saw a massive burst.
Literally 2 seconds.
It was 2 seconds after. Okay, so, and Fermi, when you look at where Fermi looks in the sky, it's a patch of about, it's a huge patch. It's 400 full moons.
No small part of the sky.
Right. And you see the full moons about the size of a nickel held at arm's length. So 400 of those, right? So you've got this big wide area and you say, okay, it probably happened there. And Fermi has another kind of cooperative instrument called integral that narrows the field just a little bit. Like it chops it down to maybe a third of that space. And both Fermi and integral saw this gamma ray burst from whatever the source was. And so that narrows it down to now, maybe 100 full moons worth of space. Now you bring in LIGO. Based on LIGO's data and the detection and the pointing of the two instruments, the two LIGO detectors, there are two very thin strips of space where this detection could have originated. And lo and behold, one of those strips overlapped with the Fermi and integral data. So now you've got it down to maybe 30 full moons of sky. Still a lot, but there's one more clue to this too. In addition to LIGO, there's another gravitational wave observatory called Virgo. It's in Italy. And Virgo didn't see anything. They didn't get a detection. Now, you might think, okay, well, does that mean that it didn't happen? Well, no, it actually means that it was in what we call a blind spot. Okay, so this happened, but Virgo couldn't see it because with the way it's lined up, the interferometer being on two axes, there's actually 4 small blind spots right around 45 degrees to the two detectors. And if the detection came from one of those 4 blind spots, Virgo wouldn't see it. And so that's basically what happened, is that this had to have happened in one of those 4 blind spots. Now you take those blind spots and you compare them to the LIGO, integral, Fermi overlap spot, and it narrows it even further to a range of about 5 full moons of sky.
And that's still huge. 5 full moons is like when you're looking for something that is new in the sky, 5 full moons is a lot of space to cover.
Okay, yes, so right. And then now the next step to go even a bit closer is to say, okay, what galaxies are out there? Because chances are this didn't happen in our own Milky Way. Chances are it happened in a distant galaxy. And so there must have been about 30 candidate galaxies. And so the amazing thing is that they all this information, these telescopes across the world are connected. They have an alert system where when something is seen, when something interesting is found, all the other telescopes can be notified and they can respond by pointing them at that event, which might be scientifically valuable. And now this is a prime example of that. And so
highly valuable.
Oh, highly valuable. So these 30 galaxies were being looked at in a bunch of different wavelengths. And sure enough, one of the astronomers, they were doing an interview and they were asking them, how are you actually doing this? And they said they were literally looking at 2 images, one that was just taken of a galaxy and one that was taken days before, and literally doing the blink test between the two of them to see if there were any changes.
Well, that's how it works, and that's still how it works for even looking for asteroids, comets, or dwarf planets in our own solar system. It's still the blink test.
Blink comparator. Yeah. Right? Those old instruments. That's how Pluto was discovered.
Now, how could, of all the galaxies that are in that section, say 30 galaxies, I mean, you need a picture to compare to, right? Because what they're looking for is a new star, a bright object that has popped up in the galaxy that would betray the existence of a collision between 2 neutron stars. Mm-hmm. And you need a compare image. We as astronomers don't collectively get together and say, okay, you're doing these galaxies this month and you're doing those galaxies this month. So they must have to do a little bit of looking to find the most recent pictures.
You know, their databases are pretty good. Like, I don't think it's that difficult to bring it up. Like, once you've identified which galaxies are in the group to look at, those databases are usually pretty quick.
Certainly with the Canadian Astrophysical Data Center, the
Yeah.
CADC, those are kept up to date. With any telescopes, any Canadian data collection is put on there like pretty quickly, at least within the last year.
Mm-hmm. Well, it doesn't. You know more about this than I do, but does it need to be a new image? Like, could it be an image of a galaxy from, 5 years ago, 10 years ago? Probably.
Yeah, it could, because what you're looking for is a new star, and the only way that's going to happen is supernova or neutron star merger or something like that. So the likelihood of one of those happening in any given galaxy on a 1 to 5 to 10 year time span is pretty small.
Yeah, definitely. So I guess it doesn't, galaxies change over billions of years. And so, I mean, long story short, they did skim through that data for 30 galaxies or however many there were in that space, and they found where it actually happened. They unbelievably, you could see it. This was, and it looked a lot like a supernova in terms of brightness. It was a spot that got brighter than the entire galaxy in which it resided, and it was clearly visible, a visible difference. And once that was discovered, now 70 different collaborations of groups around the world, different telescopes and different wavelengths across the electromagnetic spectrum, are looking at this over the course of days to see, let's see what happens. Let's gather as much data as we can.
Yeah, see, that's part of the importance here is that when you have something like a supernova or a merger like this, not only is the peak brightness important, but the form of the drop-off in light is important. So, for instance, when a supernova explodes, when a star collapses in on itself and explodes outward, it has a very specific kind of form. You watch the light get brighter, and then it will dim away over the period of a few, say, months, and then go to nothing, and eventually that supernova will turn into, say, a neutron star, a black hole, and there'll be a big nebula around it, and it'll be there in the sky to see. So that form, not only the peak brightness, but the drop-off in brightness, the length of time it takes to drop off is really important. It tells you what kind of object made it happen. Was it a massive star? Was it a star with lots of metal in it? Was it a binary system, et cetera, et cetera? And so that's what all these people were looking at, is the shape of the light curve after the merger.
Well, now this is a great question too, because how do we know it's neutron stars? How do we know it's not just a random supernova that we happen to find? I mean, aside from the fact that it's in the right spot at the right time, there's still 30 other galaxies, or however many. I'm making that number up.
Do you know the answer to this? Because I can only guess.
Well, let's hear your guess.
My guess, I think it has to do with the strength of the explosion. So there's a supernova. There's like classes. There's classes of nova. There's nova. There's supernova, and in the middle there's kilonova, and that's what this is. And a supernova has we understand the amount of mass required to collapse a star. We understand the physics of what will happen during the collapse and during the resulting rebound and explosion in a supernova. You know what? We should do a whole episode on supernovas. But we understand all the physics. We know how much energy is going to be released, and we know what their light curves look like. So the amount of energy released in this case was not as much when these two neutron stars merged, didn't match what a supernova explosion looked like, I think. But
so that's part of it. The other part is the gravitational wave signal.
Oh, yes, of course. Yeah.
So gravitational waves are predicted by Einstein's general relativity, and it turns out it's really not that hard to use those equations to simulate what would be produced when two black holes collide or when two neutron stars collide. And so this is how we knew that the original signal, at least the LIGO scientists knew that the original detection was from two black holes colliding, and that it was black holes with masses 29 and 36 times the mass of the sun, is that they ran simulations based on Einstein's equations and produced all of these potential patterns, these potential signals of gravitational waves. And the one that matched what we actually saw is what we said, oh, that's perfect. It fits perfectly when it's 29 and 36 solar masses, and 3 of them are completely vaporized or completely converted into gravitational wave energy. So that's how it was done with the neutron star merger as well, is they said, okay, well, look at this signal based on the intensity of it, run simulations, it fits the merger of 2 neutron stars over a period of this much time, all that stuff, and these masses, and that's how they do it.
Man, if only Einstein could be alive today.
He'd be pretty blown away.
He'd be pretty happy. I mean, he wrote that stuff was his paper on general relativity that describes the curvature of space-time and its effect on us. Was written back in 1916, 15?
Yeah.
Something like that. And it's still predicting things. And we're still measuring those predictions. We're still confirming the predictions. Although there's a whole other side to this, and that is that general relativity doesn't match other things. And that's where dark matter comes in. But we can cover that another time. I
have a question for you.
Go ahead, yeah.
Well, who cares? I know, and I'm going to ask that question pretty much every time we do this, but like, who cares that we can see 2 neutron stars merging? I mean, aside from the fact that it's pretty freaking awesome.
Okay, that was going to be my first answer.
Yeah, why does it matter if we can even see gravitational waves?
There's a lot of answers to this.
Well, what's your answer to that?
I have like 4. One
okay.
is that if we can measure gravitational waves in a manner that shows us that our understanding of general relativity is correct, meaning if we predict that if general relativity predicts that gravitational waves exist, and then we go out and measure them exactly the way it predicts them, then it really makes us feel good about the other things that we see general relativity predicting.
Oh, I like that. That's
so
good.
It backs up the theory that we've based a lot of modern astronomy on.
Yeah, it gives a lot of support to a theory that's kind of a pillar of astrophysics.
Absolutely. I think really what this does, and this was more back in 2015 with the detection of the first black hole merger, is that we are now in a point in history when astronomy isn't only about light. Because all of human history, from up until September 7, 2015, the only way we looked at the universe was through light. Right? All of our telescopes.
Well, and even until the 1970s and 80s, it was only through visible light.
Yeah, exactly. Yeah, that's a really good point. And now with LIGO and the whole gravitational wave phenomenon being detectable, we are now able to probe our universe with an entirely separate tool, completely separate from light, completely separate from what the electromagnetic spectrum can give us. And you nailed it when you were asking, how do we know that these are neutron stars? Well, if we didn't have the gravitational wave measurements from Virgo and LIGO, from LIGO, not Virgo, then we wouldn't have been able to definitively say that this is a 2 neutron star merger, because part of it was knowing the light curve of the kilonova, but part of it was also measuring the gravitational wave signal. So now it's like we've been spending the entirety of human history with a hammer, and now we have a saw as well. And
I like that. That's a good analogy.
Right? That is why I care.
We're really tired of breaking down trees with our hammer. Now that we have a saw, it's much better.
We can build houses much quicker.
Yeah. I heard somebody describe it in 2015 as we have a new sense. We could only see, but now we can hear.
Oh, that's
And-
so
and-
much more eloquent than the way
I don't know.
hammer and saws.
I like the hammer and the saw because, I think that's really good. I'm going to use that from now on.
Okay.
But
Attributed to me.
the one I want
Copyright,
to
Jesse.
add to that, and for me, the exciting thing about gravitational waves is what they can do once we get better at detecting them.
Ooh, enlighten me.
And that has to do with the Big Bang, right? The furthest back that we can see is is about 380,000 years after the Big Bang, which is when you actually the universe becomes transparent and you get the cosmic microwave background radiation, right? The afterglow. And so with gravitational waves, if we can detect very, very tiny gravitational waves, we can detect the leftover gravitational wave energy from the Big Bang. It's almost
that
like
must be on like Planck scale.
it's got to be small, right? But that's the universe, like a giant bell, is still ringing after 13.8 billion years. And if we can detect that, we should be able to probe deeper than that 380,000 years after the Big Bang and now look all the way back to the beginning of space-time.
I just had flashes of 2001: A Space Odyssey.
Cool. That's what I was going for.
That's really, I did not even realize the potential there.
Yeah, there's actually a project at the South Pole. I think they were working on that.
Is that
They're
BCAP
trying
or whatever?
maybe, yeah.
Oh,
they're
what is
they're
that?
trying to detect those gravitational waves from the Big Bang. So,
Not gravity waves?
not gravity waves.
Not gravitons?
We established this half an hour ago.
Remind me again? So, okay. Rippling of space-time as a result of the Big Bang, it would have been stretched out. I mean, the farthest one, the two black holes that merged back in 2015, it was something on the scale of 1,000th the size of a proton, and that was only 3 billion light years away. And so we're talking something 13 billion light years away,
And a lot
And-
less intense.
and a lot less.
Well,
intense.
not when it occurred.
Well, no, not when it occurred, but now after the universe is expanded out.
So maybe that's something to look into is we can look at, what are the predictions for how strong that leftover gravitational wave
That's a good
energy
question.
is.
That's your homework.
How loud is the ringing of the universe? Oh, good stuff.
That's,
So,
that's the title of the next episode.
yeah, there you go. So what are we talking about next week?
Next week it's asteroids, and that is because we recently had a flyby a couple of weeks ago or more of a relatively large-ish asteroid, and I always have a great time talking about it. I don't know about you, but I love talking about asteroids flying by Earth.
Yeah, totally.
It evokes images of Bruce Willis.
Sure. Yeah, okay. But hey, it's a good topic, and we're going to do it really well because that's what we do.
Yep, much better than Bruce Willis.
All right, until next time.
Well, that's the end of this show. Thanks for listening.
If you want to get in touch, find us on Twitter.
My handle is @JesseRogerson.
And my Twitter handle is @AstroInAction. Check out other episodes, or just keep listening to us every week.